Welcome to the 24th lecture video for Physics 4C. In this lecture set, we will look at some exam type questions involving quantum mechanics, mostly done non-relativistically. We will start with a review of topics we have covered in OpenStax University Physics Volume 3, Chapters 6 and 7, which cover the historical introduction to quantum mechanics and what bits of wave mechanics we can cover at our level. Then, we will look at two exam type problems that test your understanding of what we have covered in these chapters. This video is on the shorter side because we are not covering topics with the real interesting details, atomic physics, nuclear physics, and particle physics here. We will try to have another review video that does cover these topics with the real interesting details before this semester ends. So the part that we are covering in exam 2 is what I'm calling early quantum mechanics. So let me just write out what you are expected to know. So it would be early quantum mechanics. So in the lecture, we went through the experiments which led to some of the quantum mechanical assumptions. You should know them because I might ask you about those on the multiple choice. And as a matter of pedagogical history for development of quantum mechanics, you should know them. But you probably don't want to be writing those down in your formula sheet. You don't have enough space for that. So as a matter of just naming the names of experiments, what you should be familiar with are blackbody radiation, photoelectric effect, and the stable or model of a hydrogen atom. So those are the key things you should, me mentioning it should remind you of something. But what I definitely wouldn't do is, for example, I wouldn't write down the Planck law formula here. Even though I don't have it memorized, and you probably don't have it memorized, the thing is, I'm not going to put anything on the exam that requires you to have those memorized. Or I wouldn't really write down Wien's displacement law either. I mean, you should know what it is. I guess you should know conceptually what that means, but you don't need to have the coefficient memorized. If you somehow need to know that for answering some question, I would give that to you. So in the early quantum mechanics, the things that you things that you hopefully have memorized, but in case you don't, as a reminder of how important these things are, what you would have written in your formula sheet are these quantum mechanical assumptions that energy of certain things, photons, biggest one, comes in a quantized quantity. And the quantized amount is given by Planck's constant times frequency. And the second important relationship is the de Broglie relationship, that anything that has a momentum has a wave property associated with it that gives rise to wave interference phenomenon and all that. The momentum is given by Planck's constant divided by wavelength. So this is the gateway that takes you from something that is a wave to its particle property, or something that you traditionally thought of like a particle to its wave property. You can go either way. So these are the two most important quantum mechanical assumptions, and everything else we've done up until the week before spring break kind of relies on these. Even when we introduced the Schrödinger equation, we were relying on these relationships to kind of guess at the correct wave equation. Oh, and I guess while I'm writing this down, I should write down the second form of these that use h bar. So HF, that's the same thing as h bar omega. H over lambda, that's the same thing as h bar k. Do people remember that? Especially if you don't, this is, formula sheet is a wonderful place to have reminders for you that, the basic relationships that hopefully you have memorized, but people do forget. Like h bar, all that means is h divided by 2 pi. And the basic wave relationships, like omega is equal to 2 pi f, wave number is 2 pi over lambda, that sort of stuff. Stuff that you knew, that you are supposed to know, but may have forgotten. Let's see. There were other things we covered in early quantum mechanics. Wait, did they cover anything else? I guess as far as the basic relationships go, this is kind of it. So for the Bohr model, right? So what Kevin is talking about is the Bohr's assumption that angular momentum comes in the quantized quantity of nh bar. Or if you write it out like this, then nh over 2 pi. Sure, yeah, you should remember. So this is what I would recommend you. You should be familiar retracing what's called semi-classical analysis. And the biggest example you have is the Bohr model. Because for much of the Bohr model, you're doing classical analysis. It's a circular motion of two bodies that are attracted to each other through electrical interaction. And it's a semi-classical instead of classical because at some point along that step, you introduce this assumption. So that's something, so without promising you that I will put Bohr model on the exam because I might decide not to. If you were to review something in quantum mechanics, this is something that brings together a lot of pieces that you are supposed to know for quantum mechanics. So you should know how to do this. And it sort of comes in two pieces. The big part that I think a lot of people may need to review that I don't emphasize enough is the classical portion. Because it sort of comes down to how well did you do in physics 4a? How well did you do with the circular motion stuff and things that involve centripetal acceleration? Especially if you didn't, then you should review how those ideas are used in Bohr model. And while not forgetting the new things that are being introduced in this semester. So these are some of the biggest pieces, and with those out of the way, you should know kind of more fringe stuff. So there are special formulas that are, so I guess just to be comprehensive, I don't want to feel like you are misled if I decide to do something else. So if you look at the past exam I posted, you will see that the quantum mechanics question that's there is the infinite square well. So that's another example of semi-classical analysis. So this infinite square well, so let me call it square well. So that's another example of semi-classical analysis because for much of analyzing, let's say, energy of the particle in this box, you are using your classical intuition, the kinetic energy. But it's semi-classical because at some point you bring in the fact that it behaves like a wave. So there are only some allowed wavelengths that fit into this well. So those become the allowed energy levels. So I think these are the two big examples of semi-classical analysis, and we didn't really do anything else. So whatever I pick, it should be within those two.
So just quick question, that's also you call that particle in a box, right?
Yeah, particle in a box, yeah. So I should square well, or your textbook calls it, it always comes with a quotation mark. Particle in a box. And so for exam 2, study infinite square well, but not the finite square well. We haven't gotten to that. That's a part of chapter 7 that we haven't gotten to. We will come back to that after exam 2, because that's where it's more of wave mechanics. But speaking of wave mechanics, there are some things from wave mechanics that at least you shouldn't be surprised with. The Schrödinger equation, we did cover it. So if you see something that looks like this, which is the Schrödinger equation you have seen, the time-dependent Schrödinger equation that you have seen, then at least at a minimum, you shouldn't panic. You should feel like, oh, you have seen this somewhere before. As in, it's a differential equation, and that this describes the matter waves that we are going to deal with. That portion is not that surprising. And you have some idea, some sense that this term is representing the kinetic energy, this term is representing the potential energy, and this is representing the total energy. Just at some basic conceptual level. And with the exam 2, the most I would ask you to do anything with the Schrödinger equation is, give you a solution, tell you the equation. So I guess if you don't want to write this down in your formula, that's fine. Tell you the equation and tell you, well, verify that this is a solution, or what I'm telling you is the solution, is a solution of this differential equation. And you guys remember how to do that, right? Your exam had something like that. You just plug it in. Yeah. It's very simple. But a lot of people who don't have experience dealing with the differential equations or partial differential equations, it's so easy to get intimidated when there's no reason for you to be. Because all you have to do is take the derivatives and just do some simple algebra. So that's the level of wave mechanics you would see on your exam 2. The more sophisticated things, we are reserving it for your exam 3. We'll come back to all of that later. And I don't know if I should write down some special case formulas. So I guess for the Bohr model and particle in a box, there are some special case formulas that, like Bohr quantized the radius, velocity, energies. Those things are good special case formulas to have in the formula sheet. If for nothing else, to double check that any answers you derive are correct. Oh, I almost forgot. So this is actually something that's kind of missing in the posted sample exam. And I want to highlight this and make sure that no one misses it. This is sort of why I covered the topics in the order we did it this semester. So the thing that I want to make sure that everyone remembers to have reviewed, have in your formula sheet, know how to use it, is Compton scattering. So Compton scattering is one case where you really need to have the formula that's derived in the textbook. If you're trying to derive it in the exam, it's going to take you too long because it's a collision analysis that takes into account the special relativity. So the formula that's derived in your book is wavelength of the scattered photon minus the wavelength of the incident photon is equal to the what's called the Compton wavelength of the particle, h over mc. And in lecture, we did a special case where it's a straight back. But in your homework, you've seen you've had the questions where you had to use the more general formula, where it's 1 minus cosine. This theta is the angle between the incident photon and the outgoing photon. Okay? So you should have this Compton scattering formula in your formula sheet somewhere, because I really don't expect you to derive this on the exam. And you should know its a physical meaning so that you know how to answer questions that are based on this. Okay? So exam 3 review. And the biggest portion of that is quantum mechanics. And I guess to be explicit, maybe I should say wave mechanics, because we are not talking about black body radiation. We are not talking about photoelectric effect. We are talking about the actual machinery of quantum mechanics, Schrödinger equation, which is wave equation. So to emphasize that, I'll just say wave mechanics. That doesn't mean I want you to forget about all the kind of intuitive basics that we covered in chapter 6. You should still remember those intuitive basics. So let me just spell out what those intuitive basics from chapter 6 that you ought to remember are. It really starts with, in our context, de Broglie relationship, that momentum is related to the wavelength by h over lambda. And in the context of wave mechanics, we can actually expand on this a little bit more. That momentum is given by h bar times wave number. And the reason I prefer this form over this in wave mechanics is because of the hint at the operator form of the momentum. The momentum operator is h bar over I, partial derivative with respect to position. Or technically, this is the x momentum operator. If you're talking about the y or the g component of momentum, this will be y or g. Yeah? So this reaches all the way back to chapter 6 because this was chapter 6 material. But having that good intuition is important for how well can you use the mathematical machinery. Good. And the other thing that we covered was energy. So energy, it came up as people were doing photoelectric effect or whatnot, is the quantized energy is Planck's constant times frequency, or the version I prefer is h bar times omega, because this is the form that's more commonly in mathematical expressions. And once again, this is hinting at the operator form of energy, which is the energy operator is there a minus? No minus. I h bar partial derivative with respect to time. Okay. Let's see, what else do you need to remember from chapter 6? I guess it's just the one big thing. The uncertainty principle at our level, it's more of an intuitive principle than something that we are going to do a lot of technical, complicated calculations with. So let me just put uncertainty principle under this rubric. Uncertainty principle. Actually, it works the other way. Let me just. So the one that you guys actually had to know for exam 2, and that's the basic uncertainty principle, is the one involving momentum and position. That difference, the uncertainty in momentum times uncertainty in position is greater than or equal to h bar over 2. And this is something, I guess I've never written an exam question that looks like this. But this is only my second time teaching this class, so I could actually write a question that you can do. If I were to, then this is an actual detailed calculation you can do. Because these delta p and delta x, they can be precisely defined as the standard deviation. Meaning, I'm going to erase this in a bit. Delta p squared. Really what that is so standard deviation squared or variance. So it'll be take the momentum for some ith thing, subtract out the average momentum, right? Take this squared, and then average it again. That gives you the variance. And I guess I can just stop there. And when you go through some simple kind of statistical or algebra with the statistics in mind, what this simplifies into is expectation value of momentum squared minus square of the expectation value of momentum. Can you see the difference? Yes? Or in other words, in the simple case, like with the infinite square, well, that's the context where I'm thinking about this, just thinking out loud. In the context where average momentum is 0, essentially this uncertainty squared is the expectation value of momentum squared. So with that in mind, you could actually express this something like this. Expectation value of momentum squared times expectation value of position squared is greater than or equal to h bar squared over 4. And so that's why I have been emphasizing this momentum position uncertainty more. It's something that's actually accessible at your level. Not as simply, this is approximately greater than or equal to, but like you can do an exact calculation and show that for under certain minimum uncertainty configuration, this equality is actually met. And that there's no situation where you can go below that minimum uncertainty. But because you may be using this for some of the particle physics stuff, let me just spell it out. There's the energy time uncertainty principle. And this is something you will see when you take upper division quantum mechanics. Despite their kind of apparent similarity, the mathematical basis of it is very different. So the energy times delta T is greater than or equal to h bar over 2. And I don't know how your textbook derives it. So what I will say is that assigning meaning to these are easy, because momentum is a physical observable. It's a quantity you can measure. The position is also physical observable. It's something you can measure. So you get uncertainty on those measurables, then you get that. Energy is a measurable, that's fine. Time is not a measurable. So here really the biggest difficulty you would run into, well, not difficulty, the subtlety that I want you to be careful with, that's why I didn't deal with this at all, is the subtlety of dealing correctly with delta T. And what I will tell you is that in the context that you will be using it for particle physics, this delta T will always be lifetime of an unstable particle. And at least that's one meaning of delta T that's not wrong. No, that's not wrong. Yeah, that is not wrong. So this is something that you may see on your exam. In a very minor context, it wouldn't be, because particle physics already is only like 30% of your exam, and I don't want to waste too much of the 30% on this. All right. Yeah. So these are more intuitive stuff where you're not solving any differential equations, you're not doing anything that's super difficult, other than some hint at the upcoming differential equations. So that's why this is the chapter 6 material. This is something that should sound familiar to you. If not, review it or something. But the bulk of your exam will be on wave mechanics. Or rather, the way to describe it is, it starts with the Schrödinger equation. And in fact, I would say the time-independent Schrödinger equation. Because when it comes down to wave mechanics, it's really going to be the energy eigenstates, the energy eigenstates that I can actually ask you about. So I would say your biggest focus ought to be on the time-independent Schrödinger equation. I guess you could do it with a time-dependent Schrödinger equation, but I think it's big enough of a pretension on our part to pretend that you guys know fully well how to solve ordinary differential equations. Like some of you do, but like all that we do in this class to solve ordinary differential equations, we guess a solution and check. I think that's big enough of a pretension that if we start doing time-dependent Schrödinger equation, then we have to pretend that you guys know how to deal with the PDEs, partial differential equations, and I think that's an upper division level math. So that's what I'm trying to avoid. So the time-independent Schrödinger equation, it looks like this. Minus h bar squared over 2m, the double position derivative, ordinary derivatives, because that's the whole point of doing time-independent version, of the wave function, just the position portion. I guess I've mentioned how the time dependence for this goes, but I don't think I'm ever going to test you on it. So, I mean, I have mentioned this, that when you have an energy eigenstate, when you have a stationary state, that the full wave function, including the time dependence of this stationary state, is given by, as a function of position and time, the position wave function times this very simple, e to the minus I e over h bar t. Like I've mentioned this, right? And yeah, there are things we can do, but I don't think I've built up this semester quite well along that line, so I won't test you on this. So we'll just stick with the time-independent Schrödinger equation. But if you were ever to take the upper division quantum mechanics, then this is something that I want you to be ready to come back to and deal with. This can actually be used. If you have two double well configuration, you can use this to kind of illustrate moving of a particle from one well to the other, back and forth. You have to do it as a superposition of two energy eigenstates. So anyways, we haven't done much of that. Maybe next time I teach this class again, we'll do some simulations or something, but not this class. So you're dealing with just the position wave function plus the potential times the position wave function is equal to energy as a scalar value, not the energy operator, which will give you the time derivative, but the eigenvalue. So we are kind of already implying we are dealing with the energy eigenstate. So an eigenvalue times the wave function. Okay? So that's the time-independent Schrödinger equation. That's really the centerpiece of chapter 7. And what I have to tell you is you should know how to solve it. Not for every situation. You should know how to solve it for constant potential. Or to be more correct, you should know how to solve it for piecewise constant potential by applying boundary conditions for piecewise constant potential. And this also includes things like infinite square well. It could include a finite square well, but I won't because, once again, it's mathematically too complicated. And because that's not the only thing that's described here, you should also know how to solve this. Not how to solve. You should know how to apply it. You should know how to use it, or better way of describing it, you should know how to verify a given solution. A good example that you may not have had a lot of practice doing, I think there were some questions on it, is the harmonic oscillator. The harmonic oscillator potential is complicated enough that I won't ever expect you to solve it. The solution to this is not a simple exponential. It's like a Gaussian exponential times a polynomial. So, but what I can expect you to do is if I give you a solution, either for ground state or maybe one of the excited states, if I want to make it more complicated. I think for homework you did it for ground state, right? Yes?
And the first excited state.
And did I do it for first excited state too?
Yeah, so ground and
Yeah, so for something like that, because once you get to the third and fourth, then you are dealing with a polynomial of multiple terms, takes too long. But for those first few states, I should be able to give it to you, tell you to demonstrate, prove that it is a solution, and find the eigenvalue or something. Not find the eigenvalue, or verify that this given eigenvalue is an actual eigenvalue. So that's a level of calculus that I think you should be able to do for this class. So that's what I mean, verify a given solution. Let's see, what else about time-independent Schrödinger equation that I haven't mentioned? I think there's a lot that's covered under these two umbrella, but that kind of covers it. Let's just see. Oh, I think, so it falls under this overall bigger umbrella. What it should be is that using the wave function and any operators that you know, like the position, momentum, and position operators. So position operator is actually very simple. It's just multiplication by x in position space. Yeah. There's something called the momentum space, which you saw a hint of in the FAT simulation lab, but I'm never going to ask you a question in momentum space, because that's more of Fourier transform, all that. I guess we are never doing Fourier transformation. You can study that on your own. So using the position, using the wave function and operators, let me just use this symbol for operator. Using wave function and operators, compute measurable quantities. So measurable quantities would be either eigenvalue. So in that case, whatever function I gave you better be an eigenfunction. If it's not, then it doesn't have an eigenvalue. Or in a more general case, you should be able to calculate the expectation value. And that's the kind of calculation that would actually tie with calculation of this type. Because what's involved here is the expectation value. And so this is actual detailed calculation, and I think it's a, so when you calculate expectation value, it is going to involve an integral. So depending on how complicated the integral is, I may need to give you integral table. But so this is at the upper range of the detailed calculation that you need to be able to do for this class. Yep. All right. So this is kind of all the detailed, very heavily mathematical content that you need to be able to cover for the exam. And I'll just tell you, up to this is probably like 40% of the exam. Because at least one free form answer question has to involve this. So that's already like, so half of 33% or 15-some percent. And there will be some multiple choice questions that also match with this, or maybe a portion of a free-form question. So this alone covers about 30% of the exam. So here I'll just go through it. I haven't actually looked at the questions at all. I do know it's gonna be one of the 5 or 6 questions that I recently programmed in, so I still have the advantage of somewhat remembering the questions. We'll see how well I can do the solutions. Let me bring up one tool in case I need to use it, Sage Math. So I'm just launching that in the background. And all right, so we are at 4:27, so we got 20 minutes. Let me get started. Okay. So it says, one of the significant accomplishments of quantum mechanics in developing a Bohr model. Okay. Yeah, I'm gonna use Wolfram Alpha because it really saves time in having to look up constants and all that sort of stuff. Okay. So it says, yeah, before we start, yeah, let's do a simple estimate. Heisenberg principle says that, right? Meaning that, yeah, on the knowing side. So let me just briefly jot down my derivation for the equation that I'll be using. So for A, we are starting out with this, and for many of these uncertainty principle calculation, we are really going to keep just the equality portion. Inequality means it can be greater, or if you have it flipped around, it can be less. And in terms of determining where the threshold is, that's always going to be determined by the equality portion of it. So I'll be treating this almost as if it's equality, but just remember it's not, so don't be surprised if they aren't equal to each other. So they gave us the delta x, and it says estimate a minimum value for the magnitude of momentum of the electron. Yeah. So I'm going to solve this for delta p for equality. So delta p is equal to h bar over 2 times the delta x. That feels right. So this is sort of how I imagine. If I have a distribution of momentum, then if I have this amount of uncertainty in it, then imagine I'm trying to get my magnitude of momentum as small as possible. So I pick the average where the average will be 0. But it'll still have some spread like this. And this spread should be associated in some way with the delta p. So that's going to be related to magnitude of momentum. That's consistent with the uncertainty principle. So so delta p is p mean is equal to delta p mean is equal to h bar over 2 times delta x, which doing the calculation from alpha is h bar divided by 2 times 1e minus 10 meters.
Yeah, and I think it'll understand the h bar as being reduced to Planck constant. Yeah. So we have yeah. So momentum, I guess it's kind of hard to say. Yeah, convenient. I think the most convenient unit is this. It's the basic SI unit. So 5.273 E minus 15 kilogram times meter per second. And I don't know if you can make a sense of that. For most of us, we don't really have number sense for numbers that small. Says the Bohr model is built on key assumption that angular momentum, yeah, takes this form. Find the minimum radius orbit. That is, yeah. Okay. So let me go through that derivation. So we are starting out with this statement that the angular momentum is quantized. And if you are thinking of like a circular orbit, the orbital angular momentum, it can't be zero. So really the value of n needs to start from 1 and so on. And I guess the first thing is it's a question of, okay, so at the minimum orbital radius, is your angular momentum smallest or largest? Let me go with bold assumption that at the minimum radius, my angular momentum that's consistent with all other things, it's going to be the smallest. In that case, it'll be just h bar or 1 h bar. So this restriction can be connected to other mechanical expressions like, so angular momentum, you could write it as rotational inertia times angular velocity, or you could write that as the displacement cross product with the p, where p is mv, so m times r cross v, and that feels more sensible just because I think it'll more directly connect to sort of orbital motion as opposed to this, which might not. So, um, so yeah, let me start by just writing this out. My angular momentum is that, and if I have the situation where this is the atomic nucleus, here's my electron that's going around in orbit, and if it's going in the direction I marked, if it's going in this direction, then the displacement r, it's a perpendicular to velocity. So I can kind of simplify it for the magnitude of this thing, which is simply going to be so m rv sine theta, where sine theta is 1 because theta is 90 degrees. So my angular momentum is m times r times v. And we are saying, according to Bohr's bold assumption, that this is going to equal to h bar. All right, let's see here. So we have this mrv is equal to h bar. And I hope you recognize that we have two unknowns, radius and velocity. So we need one more equation to kind of make sense of this. And that equation, I believe, will come from conservation of energy. So the energy of electron, it's going to be potential energy plus kinetic energy, which will be minus, it says it use this. So the Coulomb constant, which can be written as 1 over 4 pi epsilon naught, times the amount of charge at the center of the atomic nucleus, that's E, divided by r, distance. That's the expression for the electrostatic potential energy when it's been set so that at infinity that's 0. And that's the expression for potential energy, that plus 1/2 mv squared is equal to, what are they together equal to? Well, let's say this is equal to some total energy. then I could eliminate V here. I could say V is equal to H bar over MR, and when I plug it in, there will be an expression for R. Mm. Let me take one shortcut. I happen to know what this needs to equal to. And sorry, I can't justify this well right now other than to appeal to something called the Fourier theorem. I happen to know that this sum has to be half of this quantity. So it needs to be minus 1/8 pi epsilon naught times E over R. I happen to know that. Then in this expression, now I have two equations and two unknowns, R and V. So I can eliminate V and solve for R. Let me do that. So plugging in expression for V, I have 1/2 m h bar squared over m squared r squared. And imagining taking this expression and just multiplying through by r squared, this is what I'm gonna have. Minus e over 4 pi epsilon naught r plus 1/2 h bar squared over m is equal to minus e over 8 pi epsilon naught r. Collect like terms. Then, well, moving this over here, so it's like plus e over 4 pi epsilon naught r. And combining these two, I know that so this is 2/8. So this gets canceled out, this gets 1. So this becomes e r over 8 pi epsilon naught. Now I can solve this for r. Solving this for r, we get r is equal to, move all of this over, 4 pi epsilon naught h bar squared over m e. Let's plug in the numbers and see. So r is equal to 4 times pi times epsilon naught times h bar squared over m times a. When I plug this into Wolfram alpha, I have a kind of a natural test for if I made any mistakes. Because if I didn't, then this will come out in the correct unit of basic SI unit. If it doesn't, then I know I might have made some mistakes. So electron mass times elementary charge. Yep. Meter second. Yeah, I made. I see. I had a missing fact. So that's the electric potential. I need to multiply that by element. So I need this thing squared for energy. So wherever I see, I need to make sure that it's squared. So let me make that correction. Electron elementary charge squared. Yeah, that seems right. So elementary charge squared, that's equal to 5.29 times 10 to the power of minus 11 meter. Yeah, I think that resembles the value I remember. And after the time runs out, let me see if I can justify what I did here. So for now, I'm appealing to my knowledge of something called the Fourier theorem, but I realize that's not the best justification, so let me come back to it in a bit. It asks, what is the kinetic energy of the electron in the orbit you calculated in B? So that is actually a lot easier. If I say this, so I happen to know through knowing this, 1 half mv squared is going to equal this thing positive, 1/8 pi epsilon naught e squared over r. So let me calculate this. This I can calculate without having to calculate v first. So, so let me do that. So I have 1 over 8 pi epsilon naught. So for in place of r, let me just put this whole thing. So 1 pi epsilon naught, and where there's r would be, I'll say this thing. Okay, so times elementary charge squared. And if I didn't make any algebra mistakes, this will give me an answer in unit of energy. Good. So the kinetic energy here will be 13.6061 eV. Yeah. So the kinetic energy here in terms of expression, that's going to be 1 over 8 pi epsilon naught times elementary charge, or sorry, E squared divided by r, where r is the orbital radius calculated above. This kinetic energy is equal to plus 13.61 eV. And that makes sense because the potential energy will be twice minus this. So when you add them together, you get minus 13.6 eV that you might remember from Bohr energy levels. What is the magnitude of the momentum of the electron in this orbit? Okay. Yeah, I should have just calculated the V. Okay, so let's do this. I need an expression for mv. So what I can do is I can actually rewrite this left-hand side as p squared over 2m. Then I can rewrite this to this. Solve this for p, momentum. Then what I have is p is a square root of 2m times all of this. E squared over 8 pi epsilon naught r. So let's put it this way. P is equal to square root of 2 times m times kinetic energy, where kinetic energy is the kinetic energy calculated above. And I need to plug in the numbers. So this is the kinetic energy calculated above. 2 times electron mass times that. Okay, square root of all that. And again, if I didn't make any mistakes, it'll correctly give me something in unit of kilogram, meter per second. So P is equal to 1.993 times 10 to the power minus 24 kilogram times meter per second. Yeah. Okay, how much time do I have? 2 minutes. So justifying that leap that I made of simply using virial theorem. How can I do that without? So I think what I need to use for this part. So let me do it this way. Yeah, I remember. So this is how I should have done it. So instead of using justifying the real theorem, I kind of misremembered the step. So really to make the connection of some of the mechanical parameters and the orbital size r, instead of jumping to this consideration of energy, what I should have jumped to is centripetal force. So centripetal force says this, that if I have a particle moving at some speed v, then the centripetal force expression mv squared is given by mv squared over r. This is the mass times the centripetal acceleration. And in the case of hydrogen atom, this centripetal force is given by the electrostatic force, 1 over 4 pi epsilon naught times the product of charges divided by r squared. Yeah, that's what I should have done. So, so this is one equation involving um, r and v, one, and I had that other equation involving r and v, mvr, the angular momentum is equal to h bar 2. So, so we can in these two equations now we can eliminate v, and we should still get the same expression because these mechanical relationships are kind of they duplicate each other. So let me do it this way: solving this for v, which I've done before, h bar over mr. When I plug that in there, what I get for the left hand side is m times h bar squared over m squared r squared divided by r. That's equal to the right hand side, e squared over 4 pi epsilon naught r squared. Let me cancel out the things that cancel. Then solving for r, the sole factor of r here, then you end up with r is equal to 4 pi epsilon naught h bar squared over me squared, which is what I derived up above using different set of expressions and more advanced thing than what's necessary for this. Yeah. So this is how I would recommend that you do it. So let me do it this way. For the attached work, where I have time to organize, I don't necessarily have to do the same thing that I did when I was under stress. So I guess what I would do is, okay, I don't really need to appeal to the energy of the electron. So at least not for part B. Let me paste in part A. And for part B, we have this piece. And then I'll have to select the right part. So this part is duplicated. So let me not have that again. I think I can copy this portion. And I think that will connect. So I have that expression. Well, the numbering for the equation is a little bit off. So let me just number this as 2, since the other equation was already numbered as 1. I have C and D. And as my usual advice, you should do more organizing than what I'm doing right now, which is very minimal. It's all right. I think that's everything. I think there's some nested div issue. Let me just get rid of that. I think I might have gotten rid of. I have A, B. Yeah, that's the last one. All right, so that's it. Save work and continue. So, so this is a four model question, and oh, I guess did it? Oh, I forgot about that. So let me just look at it. So this answer that I got, comparing it to the answer in A above, they are actually quite similar. So when you look at this, 2 times 10 to the minus 24, that's comparable. It's within a factor of 4. Maybe not then. Okay, let's put it this way. The amount of momentum here, that's larger than the minimum momentum uncertainty here. So I would have been in trouble if the magnitude of momentum here was less than the magnitude of the momentum uncertainty here, because it's as it's going in around in circles, the momentum uncertainty would be double the magnitude. So so the fact that this is larger then what's up here, that's consistent with Heisenberg uncertainty principle. The electron in orbit around the nucleus, it doesn't cause an issue with the Heisenberg uncertainty principle. So, all right, I think that's it. So, okay, so let me do the demo of the freeform time assessment. Now, I haven't looked ahead at the question, so it's possible that I'll get the one question that I've already done. If I get that, then I will reset the attempt and then do it again. So we'll see. Let's cross fingers and hope that we don't get the one question that I've done before. And as a reminder, 20 minutes is a really short amount of time, so make sure you're ready to focus on the question when you start the timer, because even I have to make sure I don't dawdle and waste too much time. So with that, let me start. Good, that's not the question I've done, so I can do it. Or I should do it. Let's see if I can do it. I didn't study, so yeah, that's a simple harmonic oscillator. Good. Particle of mass can be used model. Is okay. Show that the wave function. All right. Yeah. I wouldn't ask you to solve it, but I would ask you to verify that something is so. Let me do it this way. So I would verify it by plugging in the solution to the time-independent Schrödinger equation. Yeah, because I didn't say how to do it. Yeah. The math work is shown in attached work. It involves taking two derivatives with respect to x, and the rest is algebra. I'm giving this discretion because it's my constant thing that I say to people. Your answer submitted within the time limit should give me some indication of how to anchor it to the work you attach. So that's why I'm following my own advice. So you are given the solution, which is this. And the Schrödinger equation says minus h bar squared over 2m. This is a time-independent Schrödinger equation plus v of x. Now I need to plug in v of x. So let me have a copy of that. So v of x would be, let me use the last version. That's actually the more useful one. So the question is trying to help you. So that is equal to the energy of the state psi x. So only the energy eigenstates is a solution to this time-independent Schrödinger equation. So what I need to do is I need this quantity. I need the double position derivative to plug it in and do the rest of the calculation. So let me just take the first derivative of psi. I'm just going to do that in my head, looking at it. Okay, I get a back. I get the exponential back. And I have to apply chain rule. So I'm taking the derivative of the outside, which gives me the same thing back. It's an exponential. And now I have to take the derivative of the inside. So it'll give me minus, factor of 2 comes down, 2m omega x over 2h bar, 2's cancel. And now we are done. I guess there isn't really simplifying this further. So let's take the second derivative. So for second derivative, I just take the derivative of this expression, and I'm gonna have to use product rule. Yeah, it gets to be kind of long. So a is fine. The product rule. So I had to take derivative of this exponential first. That I can kind of just save a little bit of work by just copying this. I already had that. So taking the derivative of exponential again, I would get exp minus m omega x squared over 2h bar times this factor that came down before, minus m omega x over h bar. And because there was already a factor of this from before, it becomes that squared. Now for the product rule, so I took the derivative of the first term times that. Now I have the product of the first term itself, just that, not the derivative, not that it looks different. because it's exponential, and then I need to take the derivative of this, which will give me minus m omega over h bar, because it's just linear in x. All right, that looks good so far. So the rest is algebra. I need to plug this in. So I have, let me just assemble everything together. Minus h bar squared over 2m, all of this, and I think I can simplify a little bit. I can factor out exponential of minus m omega x squared over 2h bar because they're in both terms. And then for what's here, it'll be, let me write out, it's just distribute the square. It looks like that, minus m omega over h bar. And then I need to do plus the potential, plus 1/2 m omega squared x squared. Oh, I made a mistake here. There's actually psi x there. So I need to multiply that by the psi x, which is a exponential of minus m omega x squared over 2h bar. And all of this should equal energy level times psi x, which is a exponential of minus m omega x squared over 2h bar. Yeah, so looking at this, we get to cancel out some things. A cancels out, the exponential cancels out. So it actually gives you an expression for energy. So according to this, our energy level should be equal to, let's just write it all out. So I'm gonna distribute h bar squared over 2m there. So I get the first term becomes minus m omega squared x squared over 2 h bar squared and m having been cancelled out, and then plus I get h bar, m's cancel out, omega over 2, okay, plus we have 1/2 m omega squared x squared from here. So this actually cancels out with that, and we get a constant value of h bar omega over 2. Oh, this must be the ground state. Did I already say it's ground state? Yeah, so it's ground state. So energy is equal to h bar times omega over 2. This must be the ground state. Good. And I wouldn't give you actually any of the excited states because this calculation becomes so time consuming once it's any kind of level of complexity. Yeah, it took me 8 minutes. I gotta go faster. Okay, wave function given in A, find the normalization constant so that, you gotta, we set a integral of psi ax from x equals minus infinity to x equals plus infinity, and choose a that would make the integral equal to 1. So let me do that work here because it's a long algebra or calculus. I don't have confidence that I can type it out fast enough. So psi a is still this. And because it's a real function, the absolute value squared doesn't actually do anything complicated. So let me do negative infinity to infinity, psi a x squared dx is equal to, go from negative infinity to infinity, a squared. I'm going to assume a is real, or I'll choose a real value of a, real and positive, and then exponential of squared, so I get minus m omega x squared over h bar. Because this thing squared, exponential algebra, squared comes in as a factor here, and that would cancel that. So that dx, okay, this is where I think we need this definite integral formula. So they gave us this formula. So let me write that down. Negative infinity to positive infinity, e to the minus alpha x squared dx is equal to square root of pi over alpha. So here we are choosing to say our alpha is equal to m omega over h bar, not squared, just h bar. So with the choice of alpha, we can just directly apply this to get a squared pulls out of the integral, and evaluating the integral from negative infinity to infinity using this formula, it becomes the square root of pi over the alpha, which is m omega over h bar. Yeah. So we want to say this is equal to 1, and then solve for a, or solve for a squared first. A squared should be equal to square root of, doing the algebra in my head, m omega over h bar pi. So that's a squared of. So a must be this thing, m omega over h bar pi raised to the power over 1/4. So a is equal to m times omega divided by h bar times pi raised to the power of 1/4. All right, good. Let's see how much time. 9 minutes. Yeah. All right. Plot below shows that for the excited student. Okay, point out the features of the consistent with the correspondence principle. So that means what this means is correspondence principle says that for high values of n, the behavior of quantum mechanical solution approaches the behavior of a classical solution. So one thing we have to say, so we see that the particle is more likely to be found around the classical turning point, and that is consistent with the classical velocity of the particle being lower near the turning point, so the particle spends more time there. Point out the features of equidistant correspondence principle. What else? Also, the particle isn't very likely to be found much beyond the classical turning point. Same feature as what one would expect classically, except that the quantum mechanical solution involves a little bit of tunneling from the wave behavior. All right. Let's see. Anything else? I think that might be it. And least, yeah, I think I've said the most important things. So, got 7 minutes. Let's look at this one. The plot below represents the measurements of the energy levels of the epsilon meson. The first three have these energies. Okay. Assuming then strong force interaction at bottom. All right. Energy level epsilon meson. All right. So I'm so this is the reasoning process I would go through. So yeah, it's kind of too advanced for this class. But what I have to say is, I know the energy levels of the simple harmonic oscillator, m plus 1/2 h bar omega, which means the difference between energy levels of adjacent levels is h bar omega. So this is how I can interpret this plot. Let me just get a thing of that. So what I can say is, well, looking at this plot, I can kind of see the energy differences from the given numbers. The kind of the energy difference from here to here, delta E 1, 2, let's say, is 10,023 minus 9460. So that should be 563 MeV, I think. The 563, I get that back. Yeah, I think that's good. And the next difference, which ideally would have been the same, but here they are not. So we'll just roll with that. The difference in energy between levels 2 and 3 is 10, 355 minus that. So that looks like a 332 MeV. Okay, so I would like to say, let's just use the average energy difference. So this is a complicated setup. We are trying to model it as a simple harmonic oscillator. It's not actually simple harmonic oscillator. So we'll say, okay, the average is 563 plus 332 divided by 2. That's 895 divided by 2. So that's 4. I really shouldn't be doing this in my head. 4, is that 7.5? 2, 14. Yeah, I think it's 447.5 MeV. So we'll say, assuming that, so the average energy difference between levels is delta is equal to 447.5 MeV. Interpreting this as delta E in h bar omega, see how that should work. The angular frequency omega would be omega is equal to 447.5 MeV divided by h bar. This I would just do in Wolfram alpha. So it involves constants of 7.5 MeV per h bar. So that would give me 6.80 times 10 to the 23. 6.80 times 10 to the 23. Now it's not actually hertz, it's radians per second, because it's omega. Yeah, that's probably right. And yeah. All right, how much time? 3 minutes. Yeah, so I think that's all right. Let me use the remaining 3 minutes to attach my work, and then we'll submit it, and we'll look at the answer key to make sure I didn't make any mistake. I think I've shared this before that, usually like topics we cover in mechanics, physics 4A, I don't need any prep. You can wake me up in the middle of the night, have me work on something, I can do fine. It's like a second nature to me. Once you start getting into like physics 4B, physics 4C topic, many of them, if I didn't have chance to prepare ahead of time, I might make mistakes. I might misremember certain things. That's entirely possible. And when it happens, it is embarrassing, not for just being wrong, but for not having prepared, not knowing myself well enough to know if I need to prepare or not. But I think I've done correctly. We'll see. Yeah, let me just submit and end here, and then we'll look at the answer key. Yeah, that's all that. I can still change my work if I want. If I don't, save work and continue. I can still change my work if I reload here. There's add work thing here. So I'm gonna go in as instructor, so that I can bring up test the student's attempt and show you the answer key that way. Otherwise, I gotta do a lot more complicated things. This is easier. So let me go into the freeform assessment for quantum mechanics. The only person who's done it so far is test the student. Great. And this is test the student's attempt there with an answer key box. So I have done that. What does my answer key look like? Oh, I typed it all in. Didn't just scan my work. Yeah, so that's the work you need to go through. Gotta go the calculus and the algebra, and you get that. Yeah, good. And yeah, that's what I said. Let's see, m omega pi h bar raised to power. Great. Yeah, that's the correct answer. I must have done this correctly. And let's see if I forgot anything here that's in the answer key. This is kind of open-ended. I think as long as you say this, that's completely correct. The other things you might bring in, that there's gonna be individual variations. It becomes larger on turning point, more like, yeah, that's the important thing. Yeah, good. I did that. Yeah, good. Now finally, did I get the right answer here? Let's check. Yeah, good. 6.80, 10 to 23. Great. Yeah, that's correct. So yeah, that's so if I were grading, I would give it full credit, but I'm not grading, so it's fine. Yeah, so that's another demo of your quantum mechanics question dealing with a simple harmonic oscillator potential, and it's potentially challenging. The math you have to do for parts A and B take a long time. You kind of have to know exactly what you're doing, and hopefully, if you watch this, took some time to understand it, then that helped you. If you got the exact same question as here. So, all right, thank you.